Welcome everyone to the week 9 of this tutorial session of this Sobolev space and partial differential course. In this week, the you guys have studied about the this application of this Lax-Milgram lemma and there is stem features theorem and all. And with the help of that, we have seen that we can show the existence of solutions of some PDs which can be variationally uh, which can be translated into a variational setup. So, and then we see some operators, some applications of that from Laplacian to biharmonic operator, and so on and so forth. And then we saw the Galeckian method, uh, and that is a method to again show the existence solution and the methodology we have seen in with the help of an example. So in today's session, we will again see some nice applications of this Lax-Milgram lemma mainly, and then some question based on the Galeckian method. So some deductions which we are getting. So that's the plan for today. So without further ado, let's start our session. We will see some of the PD which can be again solved with help of the Lax-Milgram lemma. The first question, we let I equal to -1 to 1. Then consider the bilinear form defined on H01 I by, this is the bilinear form which I'm considering, integration over I u dash v dash plus uv minus lambda u naught v, where I'm taking lambda belongs to R to be fixed with some constant. First thing we'd like to show is check that AUV is a continuous bilinear form on H01 I. First of all, we have to see the hypothesis of Lax-Milgram lemma to be satisfied. So as we can see, we have this pointwise term to be here in our bilinear form. So we know that there's a inclusion of this Sobolev space into the L infinity space whenever we have this dimension to be n to be equal to 1. So we like basically the pointwise value of these Sobolev functions makes sense when we are in dimension 1 because of the absolute continuity of these functions. So let's consider u0, and then u0 can be written as, if you can see, since the u belongs to 0 and I, and I is going to -1 to 1. So the u0 can be written as u0 minus u minus 1, and this whole can be written as -1 to 1, 1 to 0, u dash t dt. So this u dash t is actually the derivative with respect to the continuous representative. So, and we have this equality in almost every sense, and basically we are replacing a function u with its continuous representative. So in that sense, we are taking the equality here. So we have this. So what this implies? This implies the mod of u0 as less than equal to -1 to 0 u dash t dt. also. So here we are using one technique. So like to have a better constant on the right hand side. So like one can have, so what I can write, I can again write u0 as, so it's like minus u0 as u1 minus u0. This is again the integration from 0 to 1. And again u dash t dt. And this implies the mod of again u0 has to be less than equal to the integration from 0 to 1 of mod of u dash t dt. So adding these, we get that the mod of u0 has to be less than equal to the integration from minus 1 to 1 mod u dash t dt. And find this whole can be written as less than equal to the integration from minus 1 to 1 u dash t square dt all this power of half from the Held inequality or the Cauchy-Schwarz inequality, and minus 1 to 1, and this will be 1 dt whole power of half, which is the square root of 2. So this square root of 2 into the L2 norm of u dash. And since we are adding also, we have here twice 2 here. And this actually gives the mod of u0 to be less than equal to 1 by root 2 mod u dash L2 minus L2 1. So now we consider AUV, that is nothing but integration over I of u dash v dash plus uv minus lambda u0 v, right? So finally, what can I do? I can whole can be written as, so again using the Elder inequality, we have this to be u dash square. So the mod u dash square whole is power of half integration over I v dash square whole is power of half plus integration of I of mod u square whole is power of half integration of I mod v square whole is power of half, then mod lambda, and u0 as we have seen can be rounded over by the half of L2 norm of u dash, and then this whole thing will be just an integral. The remaining portion will be just an integral of v only. And then here I can use again the Held inequality to get the same bound. So this is actually less than equal to twice of u dash, or I can just write the h01 norm into the h01 norm. And by pointer is the second thing also we can handle by the same thing. So it will be a Poincare constant also be there actually. So let's better write a constant here only. Define the system, the Held inequality. And this is Poincare plus Helder So mod lambda by 2 u dash L2 of minus 1 to 1, and then we have this again. So this will be L2 norm of v minus square root of 2 will be here. And eventually that again can be again the same application of point current. We have this another constant C1 times the this norm, and that's not arm of v. We have this. So this gives continuity of the bilinear forms. So as part 2 of this question, we have to show the cohesivity. So let's prove that if mod lambda is less than 2, then for every f in L2I, there exists a unique solution found H2I intersection H0I of the problem minus u double dash plus u is lambda u0 equal to f on I and u minus 1 u1 equal to 0. So clearly we can associate one bilinear form associated to this problem. So for that, so the bilinear form is nothing but which I've considered above. So all we have to show that this will have a solution is by just proving that the bilinear form is cohesive for this range of lambda. So let's consider AUU only, and we will see that what can we do to have cohesivity. So AUU is nothing but integration of I of u dash square plus u square minus lambda u0 u. So this is my bilinear form. So we need to consider this thing. So consider lambda integration of I of u0 and then just u. So I can use this AMGM inequality here. So this is lambda times 2 of integration of I of mod u naught square and plus integration over I of this u square. We can have this from AMGM. Now we will use this L infinity bound which we have proved above. So this thing is the mod u0 actually was bounded above as you have seen by the 1 by square root of this thing. So using this, this is nothing but 1 by 2 and u dash L2 minus 1 to 1 square plus integration I of mod u square. This and all this give rise to this thing that lambda and using all this estimate in our above we can use directly put this thing. This will give a u to be greater than equal to integration of I of u dash whole square bracket mod u dash square mod u dash square, and then we have this 1 minus lambda over 4 and integration I of mod u square of 1 minus lambda by 2. So once we have this, since my mod lambda is less than 2, so this whole thing can be eventually done in terms of norm only then, and it has coefficients to be positive because my mod lambda is less than 2. So this will give directly that a UV is cohesive. So this gives cohesive, and once we have the cohesivity, then by the Lax Milgram lemma, they exist. Uh, then for any f in L2I, there exists a unique weak solution U of the following. And what is this? This is actually nothing but integration I of U dash V dash plus UV and then minus lambda U0 V. And this is equal to this integration F times V I, and that this holds for all V with the V in H naught 1, I and I being the interval -1 to 1. Moreover, by the standard regularity is that we can also reduce that this Q will eventually lie in the H2 space. So this actually gives just U to be in the H naught 1 I, but like so we can like for the time being assume that this can be proved, but once that is there, we can assume. But by regularity results can be proved. We have U to be in H2I space. And actually that is not very hard to see because we can write all of this thing as integration I of u dash v dash is equal to nothing but integration I of f minus u plus lambda u 0 whole times v, and this holds for all v in h naught 1I. So in fact, this holds for all the CC infinity functions. So this is a function which belongs to L to I, and this is actually nothing but the definition of weak derivative of u dash, and the still implies u has to be in h2 I, and once that is there, therefore we have u to be in the h naught 1I intersection h2I. The next part, the next part we have here, we would like to show is that. So the solution actually we get from this Lax-Milgram lemma has one deficiency, and that is that we cannot still claim that this solution is to be non-trivial. So we can see that this solution, we have trivial solution, and like uh, like when my f is 0. So like we are somehow interested in getting the unique solution or the non-trivial solution whenever my f is to be 0. So to prove that, we have this some series of questions prove that there exists a unique value lambda equal to lambda naught, which belongs to R, to be determined explicitly such that the problem minus u double dash plus u equal to lambda times u0 on I, and we have u minus 1 equal to u1 equal to 0 admits a solution to which is not identically equal to 0. So we have to prove this. So we need to consider two cases. First, if u0 turns out to be 0 only, then we have u double dash minus u double dash plus u equal to 0 only on I. And on the boundary points, we have value to be 0. But this is just a linear second order OD which we can solve. And in fact, the corresponding characteristic equation is minus m square plus 1 equal to 0, and this implies nothing but m equal to plus minus 1. So first, so the general solution is Qx equal to some C1 times e raised to the power of x plus C2 times e raised to the power of minus x. But we have initial conditions, but U1 and U minus both are 0. But this basically implies 0 is equal to C1 plus C2. So C1 into e raised to the power of 1 plus C2 into e raised to the power of minus 1. And again, this C1 times e raised to the power of minus 1 plus C2 times e raised to the power of 1. And this whole thing can be written as just a system e minus 1 e raised to the power of minus 1 e into C1 C2 equal to 0. But let's say this matrix A e minus 1 e minus 1 e is invertible. So we have only the trivial solution. Thus, we have Ux equal to identical to 0. So we have a contradiction because we want non-trivial solutions. So consider the case U0 to be non-zero. So we are in this situation. So what we like to do, we have this equation minus u double dash plus u equal to lambda times u0 on I and u minus 1 u1 equal to 0. Now, since u0 is non-zero, I can divide by u0, and this basically implies in because of linearity, the whole can consider u whole divided by lambda u0 double dash u divided by lambda u0 to 1. And again, we have this since u minus 1 is 0, so this is same as to be 0. So we can consider the problem. We can consider the problem minus phi double dash plus phi equal to 1 on I, deriving the interval minus 1 to 1, and use phi minus 1 equal to phi 1 equal to 0. So now we have this particular OD, and again, this is one can solve. So this is a non-homogeneous OD, but we know the general solution can be written as the sum of homogeneous plus non-homogeneous solution. So first, we compute the particular solutions of phi p. So like on observation, we can directly see that we need a particular solution of this phi p. Like we don't really need the phi p to satisfy the boundary problem, the boundary values. We just need it has to satisfy the OD. So phi p have to satisfy minus phi p double dash plus phi p equal to 1. So, but on observation, we can see we can take this. We can take phi p equal to 1, identically equal to 1 only. Next, phi h be the homogeneous Be the solution of the homo be a solution of the corresponding homogeneous equation. Then, as we saw above, we have this thing that phi h x has to be something c1 e to the power of x plus c2 into e to the power of minus x. So, general solution is phi is nothing but equal to phi h plus phi p, which is nothing but c1 e to the power of x plus c2 to the power of e minus x plus 1. So we need to this evaluate these constants, this c1 and c2. But we have what we know, phi of minus 1 and phi of 1 both are 0 only. So what do we have? First we have c1 e plus c2 e raised to power minus 1 equal to minus 1. And we have a c1 e raised to power of minus 1 plus c2 times e raised to power 1 equal to again minus 1. So this again can be written in terms of matrix terms. So this is e raised to power minus 1, e raised to power minus 1, e times c1, c2 to minus 1, minus 1. And finally, we have c1, c2. It's nothing but equals to the inverse of this matrix. So e inverse, e inverse, e whole inverse, minus 1, minus 1. So this is nothing but 1 upon the denominator of this matrix, which is e square minus 1 upon e raised to the power square, e raised to the power 2 times e minus e to the power minus 1 minus e. So this is the inverse. 1, 1, and we can have minus going to be multiplied here. So this is e square into e raised to the power of 4 minus 1. This is e minus e raised to the power of minus 1. And this is again the same thing, e minus e raised to the power minus 1. Again, a minus here. Both are the same quantity. So this is nothing but minus e square minus 1, e square plus 1 into e square minus 1. The same constant being here, so this is nothing but minus e whole divided by e square plus 1, which is nothing but the same thing. Minus e whole divided by square plus 1 times 1, 1. So this is our value for constants. Plus what do we have here? We have pi equals 1 plus, in fact, minus 1 minus times divided by e square plus 1, and then this 1, 1. So these are nothing but the e raised to the power of x plus e raised to the power of minus x. This is the general solution. And since we have this two constants, we have a unique solution. But since we have a unique solution, so we have a unique solution. So let's name some equations to, let's say, star, double star, two star, and this implies double star also, has a unique solution. Moreover, we have we have uh, so we have reduced this. We have reduced this. So this is nothing but we took phi equal to u divided by lambda u naught. So in particular, we basically have here we have so between like this we have p equals u divided by lambda by u naught lambda times u at 0, but this basically means phi at 0 has to be equal to 1 upon lambda, and what is this? Nothing but lambda. In fact, let's name it to lambda naught. This is equal to 1 upon phi 0, and what is phi 0? Phi 0 is nothing but 1 upon 1 minus e times e square plus 1. This is e, not e, it's just 2 only. And this is nothing but e square plus 1, e minus 1 whole square. This is the lambda naught value, so it has to become like this only for the solution to exist uniquely. So it forces the value of lambda to be this only. Now, next we would like to see whenever this lambda is not equal to lambda naught, we can see that for any f, there exists a weak solution of our non-homogeneous problem. So the final part of this question, prove that if lambda is not equal to lambda naught, then for every f belongs to L to I, there exists a unique solution U belongs to H to I intersection H naught 1 I of 1. So how do we do this? Like we can actually see we can explicitly solve this solution. So whatever we saw that this solution that is compact operator and that thing. We will use that idea to prove that we have a unique solution. So that this compact perturbation sort of technique. So but we try to prove this. We actually consider the following linear operator is such that S is something which maps G to V, where my G is nothing but is in L2I and V belongs to H2I intersection H0 1I is the unique solution of minus V double dash plus V equal to G on I. And V minus 1, V1, this is all equal to 0. So, but idea is like we have seen with the help of the Lax Milgram, we are able to prove only the solution whenever more lambda lying in the range of -2 to 2. But we can prove something more. If my lambda is not equal to lambda naught, we can still have a existence of a unique solution. So how do we do that? We consider a corresponding, let's say star three star. So this is, or let me write it in star 3. We consider this problem, and this problem like will have a unique solution from the Lax-Milgram lemma. So this is just a standard procedure. And we saw this existence of the solution in the lectures, video lectures only from Lax-Milgram. Such unique V exists. And once that is there, and what more we have seen that so we have minus phi double dash plus phi equal to 1 and phi minus 1, phi 1. They both are 0. So phi is the solution of this thing. So what this basically implies, the S of 1, so 1 is in L2 of this -1 to 1 interval. So S of 1 is nothing but phi. So phi, since there is no such exist, we have this. Moreover, we have S of some any constant, let's say some constant, some C naught is nothing but C naught times phi only, or some constant E naught in R. Thus, in particular, what do we have? We have basically in particular S of this. If let's say if I have UF to be given lambda U0, this is nothing but S of this is lambda times lambda U0 S S1, and that is phi only. So this is lambda U0 phi. So that if we take W equal to nothing but U minus lambda U0 phi, then minus W dash W double dash SW is nothing but minus U double dash plus U. And then we have minus lambda U0. And then we have this thing minus phi double dash plus phi. And that is one only. This is nothing but minus U double dash plus U minus lambda U0. And that we know is nothing but equals to F. Thus, what do we have? Thus, we have Q minus lambda U0 phi to anything but equal to the image of my F, right? So once we have this, what we can do, we have these both our functions. We can have this evaluation at 0 and U0, 1 minus lambda phi 0, SF at 0 only. So since F is given to us, so SF is also well defined and the value at SF0 is also is something which is valid. So moreover, what do we have? We have this phi 0 is nothing but 1 upon lambda 0, which we just saw in the last part, 1 by lambda 0 only. So U0 is nothing but SF0, and this is lambda naught minus lambda times lambda naught. Since phi at 0 is nothing but 1 upon lambda naught. And since as we have this thing, also U is nothing but SF plus lambda U0 phi. So since U0 which we have evaluated is nothing but SF plus lambda naught lambda lambda naught lambda SF at 0 lambda naught minus lambda is phi. The U is nothing but turns out to be this thing, and U was the solution which we assumed has to be there, but it actually gives that U has do have a value, and this gives that U is this the desired solution. The next problem which we like to consider is another application of this Flax-Milgram lemma and this idea that the homogeneous solutions the can be uh, used to find the general solution of a non-homogeneous problem. So the problem goes like this. So assume that P belongs to C1 of 0, 1 with Px greater than equal to alpha, which is positive throughout in our interval 0, 1. And I'm taking Q to be in another continuous function over the interval 0, 1 with Qx being non-negative again for all x in our domain. And I let if V naught to be any C naught C2 solution. In fact, the unique solution of minus P V naught dash all dash plus Q V naught equal to 0 on the closed interval 0, 1 and V naught 0 is 1 and V naught 1 is again 0. So let's name this system P1. And if we set K naught equals to V naught dash at 0, the first thing which you like to check is that that not has to be less than equal to minus alpha whole divided by p. This k naught is a like v naught dash at 0 is a negative quantity. So how we do that? Since already know this v naught is a solution, so it is again it's a classical solution, but again it can be seen as a weak solution. So how do we prove this? We actually just start with the multiply 1 by v naught itself and integrate over the domain 0 1. So we have uh, integration over 0 to 1 minus p v naught dash whole dash into v naught plus integration 0 to 1 u v naught times v naught equal to 0 only. So by integration by parts, we have 0 to 1 p times v naught dash whole square minus p v naught dash into v naught, and we have to see the values at 1 and 0 plus 0 to 1 u v naught square all equal to 0, and this is nothing but integration 0 to 1 p all equal to right p at 1 v naught dash at 1 v naught at 1 minus p at 0 v naught dash at 0 and v naught at 1 is equal to nothing but integration 0 to 1 p of v naught dash whole square plus integration 0 to 1 of q times v naught square. And this is nothing but, so p1 is nothing but, we don't know, but v naught, one thing about this v naught, it has v naught at 1 is 0. So this thing actually vanishes. We are left with minus p0. V naught dash 0 is nothing but k naught only. And v01 is, sorry, v0 is 0 only. This is 0, this is 1 only. And this is integration 0 to 1 p times v naught dash whole square plus integration 0 to 1 q times v naught square. Now this is greater than equal to, so now I know that p is greater than equal to some positive constant alpha and q is also non-negative. So this integration is whole non-negative, so I can drop that integral. And this is nothing but alpha times integration 0 to 1 p naught dash whole square. Now what we can do, we have this, need a lower bound for this. Now consider this thing. The So just consider, let's say we have this v0 0 to be 1, and if like let me write this in this way, minus v0 minus 1 is minus v0, and this is nothing but v0 at 1 minus v0 at 0, and this whole thing nothing but integration from 0 to 1 of v naught dash t dt And thus this implies 1 has to be less than equal to integration of 0 to 1 v naught dash t mod t dt. This is further less than equal to the by the Cauchy's cos for the Held inequality v naught dash t mod square dt whole is power of half into integration 0 to 1 dt whole is power of half. And thus this is just implies the integration of 0 to 1 v naught dash t dt square is greater than equal to 1 only. Thus we have minus alpha p0 k naught p0 is greater than equal to alpha only, and this just implies this k naught has to be less than equal to minus alpha divided by p. Since p is non-negative, so I can divide by p0. We have a proof. And the second part of the question is consider the problem. Its name is to be 2. And what is this? This is nothing but minus pu dash whole dash plus qu equal to f on 0 1, and then u dash 0 equal to k times u0, and then u1 is nothing but 0 only, where my k belongs to R is fixed and it belongs to L2 of 0 1 is given. So the question goes like, so also assume that k is nothing but equal to k naught. So then show that 2 as a solution u belongs to h2 of 0 1 if and only integration 0 to 1 if v naught is equal to 0. So these things are if and only. So we have to prove this, and so to prove this, what we can do, we can start investigating the idea that we can take this so solution. So forward direction. So assume that two has do have a solution this thing. So you satisfy this two in the weak sense as well. And so to prove this, we can start that we have u belongs to h201 satisfies 2. That means in the weak sense we have this thing integration of 0 to 1 minus p u dash whole dash v plus integration 0 to 1 q times v equal to integration of 0 to 1 f v. So this holds. Let's not, so we'll choose v. So first we apply the integration by parts. So there's nothing but integration 0 to 1 p u dash v dash plus this is nothing but p u dash, so it's the minus only v, and we have to apply 1 and 0. 0 to 1 q u v integration 0 to 1 f p. Now since we have this thing and I'm taking we can take we can take v equal to v naught, and the above equality holds, or the equality makes sense. So this actually will imply that this equality holds integration 0 to 1 p of u dash v naught dash, and this is nothing but minus p1 u dash 1, and this is v naught 1 minus p0 u dash 0 v naught 0, then plus integration 0 to 1 q of u v naught integration 0 to 1 f v naught. So let's name this to be 3. Also, in fact, we can do much more like this. Since we know the boundary values of v naught, this is nothing but equivalent to integration 0 to 1 p of u dash v naught dash, and we know that v naught at 1 is 0, so the one thing is vanishing, and we have this p naught or p at 0 and u dash 0, and in fact u dash 0 is nothing but k times u naught, so this is nothing but k naught u at 0, and finally we have v naught at 0, and v naught at 0 is 1 only, so I can also remove here this, and finally the remaining terms to be like 0 to 1 q u v naught with integration 0 to 1 f times v naught. Right, so far so good. Now finally we let's name this to be 3 now. Now as v naught is a solution and u is also a solution, so as u naught satisfies, so in the first part u naught is this v naught is the solution of this thing 1, and in the weak sense we have this, so 1 multiplying by u and integrating, we get integration 0 to 1 minus p v naught dash whole dash u plus integration 0 to 1 q of v naught uh, u equal to 0. And this basically implies that integration 0 to 1 by integration by parts p v naught dash u dash plus uh, then again so minus, sorry, p v naught dash u, and you have to evaluate 1 and 0, integration 0 to 1 q v naught q equal to 0. So this thing, so since we have v naught we know the idea of that u1 is 0, so first term vanishes and this is 0 to 1 p v naught dash u dash, and this is nothing but plus p at 0 v naught dash at 0 and u0, and u0 is something we have, and then we have this integration 0 to 1 q v naught u equal to 0. But v naught dash k is nothing but k naught, and k naught is uh, this, so we have this something. This is the same thing we have here. So we can put this thing in 3, so we closely. So this is nothing but same as using putting this thing in 3, we deduce that like the integration 0 to 1 of f with v naught is 0 only. So this gives the proof of uh, one way. When we have already the solution of 2, we have this integration 0 to 1 f v naught to be 0 only. Right now we have to prove the other way around. And to prove the other way around, we have to use this condition. We also not v naught satisfies the that equation, the OD1. Now this px are continuous and q is also continuous. Now we have to prove the existence of some u which satisfy this 2. But now using the theory for the converse way. So by general theory of this ODs, we know that there exists a function u which satisfies this particular system minus p u dash whole dash plus q u equal to f on open interval 0 1, and u1 is 0. So this comes because q is continuous we have, and p is also continuous. So as long as we have this type of things, we have the existence of a solution. And we can also take this initial value to u1 equal to 0. So, because since there's a solution, we do have this type of thing. So next we also we have integration f with v naught of 0 to 1 to be 0. So next what we do, we we can do, but we can just take this to be, let's say, 4, and we multiply v naught with 4 to get 4, and integrating, we get integration 0 to 1 of v naught, which is 0 only, and that is nothing but equals to integration minus p u dash whole dash v naught 0 to 1 plus integration 0 to 1 q u and then v naught. And this is nothing but equal to integration 0 to 1 by integration by parts p u dash v naught dash, and then we have this bounded term p u dash v naught, and this 1 at 0 evaluated 1 at 0, integration 0 to 1 q u v naught. This is the integration 0 to 1 p u dash v naught dash. So we have this v naught to be 0, v naught at 1 to be 0. So that thing vanishes vacuously. So already we have p at 0, and also v naught at 0 is 1 only. So it's u dash at 0 plus integration 0 to 1 q u v. Finally, we again know that v naught is the solution of 1. So we multiply by u and then integrate. So this we did in the forward part. Also, we have integration 0 to 1 minus p v naught dash whole dash u plus integration 0 to 1 q v naught whole u equal to 0. And then integrating by parts, we have, let's say, name to be this to be something to be 5. So this integration 0 to 1 p v naught dash q dash and minus p v naught dash u evaluated at 1 and 0. So since we have the estimate that v naught at 0 only, so we took u at 1 to be 0, so we don't have to bother with u naught dash at 1. So this thing is nothing but q v naught u equal to 0. So this implies integration 0 to 1 p v naught dash u dash p at 0 v naught dash at 0 q at 0 plus 0 to 1 integration q v naught u to 0, and we can use this and put all of this thing in one only, putting this in 1, sorry, 5, we have p0 u dash 0 equals this is actually minus here, minus p0 p naught dash 0, or we can take this to be k naught only, k naught u at 0 equals 0 only, and this gives since p0 is non-zero, we have u dash 0 to be equal to k naught times u at 0 only. So this is the condition, extra condition, which were there, and in 2, which actually coming out naturally when we assume that the integration of 0 to 1 f v naught to be 0, and thus we have our result. So this proves our second part of the backward part of a question. So finally, we would like to have one question on based on the Gallagher method. So this Gallagher method, as we saw, is a neat way to have solution. So we try to have solutions with the help of translating our problem into a finite dimensional space, and then finding solutions there, and we have a sequence solution in the finite dimensional spaces, and then we have an approximation there, uh, for approximation we have a sequence there, and then we see finally show that solution, that sequence will have the limit, some limit, and that limit is nothing but the solution of our the original equation. So we see this curriculum method is actually have some optimality in some sense. So this problem 3 is actually gives the optimality of the Gallagher method. The question is the abstract problem reads AP is nothing but find U belongs to V such that AUV is nothing but LV for all V belongs to V. So this is the abstract problem. So we AUV is some bilinear problem. So this right, we assume A to be continuous, cohesive, bilinear form on the Hilbert space V, and L be a continuous linear functional on V. We consider the Gallagher approximation of AP given by this thing. Find UH belong to VH. VH is being some finite dimensional vector space subset of V such that A of UH, VH is nothing but L of VH for all VH in capital VH. And we know that for symmetric bilinear forms, we define the energy norm as AWW per half for which we have the cause inequality to use the cause inequality. The first thing we would like to prove is prove the Galerkin orthogonality of A of U minus the UH, which being the finite dimensional solution we have with pH equal to 0 for all VH in pH. And then second we have reduce that U minus UH of A is nothing but the infimum of all those VH in capital VH. So basically, this Galerkin solution we're getting is actually turns out to be the best solution, and if we're considering the distance of this is the closest solution from our actual solution if we're considering the space VH. So in so this is the best we can have in the finite dimensional vector space VH. The solution. The part one, we know that since we use the solution, we have AU V is equal to LV for all V in my capital V, and we have A of UH VH equal to L of VH for all VH in small VH. Now this thing actually implies that A of U comma VH, since VH is a subspace of capital VH, capital VH is subspace of V, this is L of VH for all VH in VH. So if I name this to be 1, this is to be 2, then 1 minus 2 implies only A of U comma A of U minus UH with VH is nothing but 0 only. So this is a direct consequence of this. With the part 2 for the orthogonality, we know that for all VH in the capital VH, UH minus VH lies in capital VH. So A of U minus UH as in the part above, we instead of VH, I can take UH minus VH, and this is 0 from part 1 only. Also, we consider U minus UH normal square. So this is nothing but the A of U minus UH and U minus UH. And this actually can be written as A of U minus UH and then U minus VH plus VH, and then by this thing VH minus UH. So right hand side, this by relation we're considering this thing is nothing but 0 only. This is nothing but A of U minus UH V minus U minus VH. And now using the Cauchy's possibility for uh, um, this now, which is U minus UH at A, and then we have this U minus VH will now make, and thus with this reduces whatever we want. This is nothing but u minus UH with A now is less than equal to U minus VH A, and this holds for all VH in capital VH. So I can take the infimum. So this is U minus UH A is nothing but less than equal to infimum of all those VH in capital VH. That's the U minus VH when considering the norm of A. And the other side equality follows directly from the definition. Thus we have U minus UH. A is nothing but infimum of VH belongs to VH, U minus VH. So the solution which we're getting is actually the best solution we can have in the finite dimensional space. And this proves the optimality of this numerical method. With this, we stop our session for this week. Thank you. यस। अभी तो सबसे बात करनी पड़ेगी ना पहले।